Hello guys, my name is Samuel D. Koidia. Welcome to this physics tutorials. We continue to our practical exercises, and we want to encourage you to subscribe as you follow up the lectures. Now we have the topic of discussion today is physics practical, and we're going to look at refractive index and lateral shift of a rectangular glass block. I'll be demonstrating it on the board, then we go to the practical itself. So let me look at the principle behind this in the first place. Now, some of you must have come across the word, the term refractive index, yeah? And refractive index, we said it's given by the sine, the ratio of the sine of the incident angle and the sine of the angle of refraction. And it was actually discovered by Wilbur Snell. This gentleman was able to coin a relationship, a ratio that would define the refractive index of materials, right? So the first is we're going to look at what is this refractive index and what is going to do with the ray. And remember what Newton told us about light. He said light travels in straight line, yeah, but we can also see light bending when it enters different media of different density. So these Wilbur Snell was able to look at light moving from one medium to another. So looking at the medium, we want to look at the laws that govern the bending phenomenon. It's a bending phenomenon. When I say refract, to refract means to bend. To refract means to bend. To bend. So there are laws that are governing this bending phenomenon. So what are the laws? Laws of refraction. In this case, laws of refraction. Let me just give you the theory behind what you're coming to do. So the laws of refraction states that the incident ray, so if I have a surface, let's say I have a glass block like that, and I have a normal somewhere there, and this ray is called the incident ray, so it can form an incident angle with a normal. And when the light moves from optically less dense medium entering a dense medium, let's say the light bend, it will bend, so it is going to form another angle of refraction here, and as it is moving away, it's going to move away from the normal when it is moving from a denser material and entering a less dense material. So we have three rays here so far. So I have the incident ray, and we have the refracted ray, we have the emergent ray. This is the emergent ray, and it can form the emergent angle. This is emergent ray. Now this incident ray, the normal and the refracted ray at the point of incident all are in the same plane. That's one law. We said that the incident ray, the normal and the refracted ray at the point of incident are all in that plane. So that's one law. Now that's one law of refraction. The second law was actually as a result of the experiments that Wilbur Snell did for us, which was referred to as the Snell's law. It says that the angle, the ratio of the sine of the incident angle to the refracted angle, that's the angle of refraction, and the incident angle. If I take the trigonometry sine of this divided, this a ratio is not a name of division. So if I divide this ratio, I'll have the ability of this material to bend the ray. That is what is called the refractive index. Refractive index. That is its ability of that medium where the light is entering. That ability of that medium to refract or bend the ray is what is referred to as the refractive index, and it is a ratio of two things over there. So we have the incident angle, that's the refracted angle, the ratio of the two. When you take the sine of the ratio of the two, you get that. That's the ability of, it differs from medium to medium. It could be different for water, like light moving from air to water. The way the water bend the light is different from the way the light is bent inside glass is different, and the thickness of the glass also differ, and the way the light enter inside kerosene, the way it will bend is also differ. So that ability of the light to bend in those different media is what this man was able to give us as a ratio of two things. That is the incident angle and the refracted angle. The sine of that ratio will give you the refractive index. That's a law, that's second law. So remember the laws. I'm giving you the theory behind what we're coming to do. Now we have the laws of refraction. We say it is the incident ray, the refracted ray, the normal at the point of incident all lie in the same plane. Those are the two prominent laws that are there. But the third one is there also. We have a third law which states that when light moves from optically denser medium, or for instance, let's say light move from optically less dense medium and entering a denser medium, it is going to move towards the normal and vice versa. What do I mean by that? So it means that if this is air, this light is moving from, let's say, this glass, and light is the normal, 90 degrees always. Now this light is moving from air and entering the glass. Air is less dense than glass. So because the light is entering inside that transparent glass, it is entering from a different medium to another medium of different optical density. This is lighter as compared to the density of the glass. So because the glass is denser, you are going to have two things that is going to happen. This light is a wave. Now the light, the speed of the wave, because light is electromagnetic, remember that, electromagnetic wave, and we say that wave can be classified into mechanical wave and electromagnetic wave, and we say that electromagnetic wave, an example of one of them is light, where we also categorize X-ray, gamma rays, and all of them as electromagnetic ray. So example of electromagnetic ray, that is a particular group of wave that are developed when the electric field around the earth and the magnetic field around the earth cohere at right angle to one another, interact. When they interact, they generate that group of wave, that family of wave, which we refer to as EM wave. E for electro and M for the magnetic field. So have electric and magnetic field cohere together at right angle around the earth, and those two electric fields and the magnetic fields interacting together will generate that group of wave, which we refer to as electromagnetic wave. And electromagnetic wave, an example of the electromagnetic wave was that light we're talking about here now. So now that light has the ability to change its speed as it is entering a medium of different optical density. So now it is moving from air entering glass because it is going to enter a medium that has a different density and is denser than. We expect this light to change its speed, and as your speed is changing, it is going to also change its wavelength. The frequency will not change now, but the speed will change, or because the speed has changed, the wavelength is bound to change. So let's say this was the wavelength, this is the distance between consecutive crests, is the wavelength. Now when it is entering this glass, because the glass is having a higher optical density, so this wave, which is the light, is now going to reduce its speed, and reducing its speed makes it have a smaller wavelength. So you see the wavelength here, the lambda here is small as compared to the lambda here. So this wavelength changing with respect to the speed changing will now allow this guy to bend. That is the bending phenomenon, because it's moving from a less dense medium to a denser medium. It will bend, and this time when it is bending, it's going to bend towards this normal. That's what we said, when the light moves from optically less dense medium air to a denser medium glass or water, that is it's going to move towards the normal and vice versa. So that means if it's moving from optically denser medium to a less dense medium, like for instance it's moving from glass to air, because glass is denser than air, and the light is moving from a denser medium to a less dense medium, which is air, it is going to move away from the normal. So those two concepts we are put together into the third law. The third law states that when light moves from optically less dense medium and enter a denser medium, it is going to move towards the normal and vice versa. It means that when it's moving from denser medium to less dense medium, it will move away from the normal. That is a law, and this law is going to be saying in what we're coming to do. So this is basically the laws behind what we are coming to do right now here. So we have the first, we said the incident ray, the normal, the refracted ray at the point of incident all lie in the same plane, and we said that Willy Grossmel discovered this. He said that there is a ratio. He discovered after the experiment, he took series of incident angles here and series of refracted angles there and tried to plot a graph, and he was able to draw a graph, and that graph, the gradient of that graph, the slope of that graph was what was given to this. So if you do the math here, if you can find out that if I now have sine I, if I cross multiply here, I have sine I is equals to refractive index sine R. So if you do the math here, you will now see that if you compare y equals to mx plus c, and if you plot this on the x-axis, that is the I, that is sine R on that, x-axis and sine I on that y-axis, if you get a straight line. So if you do the gradient of that straight line, which is the slope, you will have the refractive index which corresponds to that. So the gradient of that line, when he did this, that gradient of the line was what signifies or stood for the refractive index. That was done with a brass nail, and this is one of the examples, the practical exercises you'll be doing. You'll be given series of incident angles, and you are expected to find, for each incident angle you discover a refracted angle, and that refracted angle, you take the sine of it and the sine of the incident angle, you plot a graph. When you plot a graph, it's going to be a straight line, because you know that from the equation it is y equals to mx plus b, which is the equation of a straight line. So when you get the gradient of that line, that gradient corresponds to the refractive index of that material. So that was what Mr. Willibrod did for us, and was able to give us the different refractive indices of different materials. Glass was 1.5 and water was 1.3, and we have for kerosene 1.2 and so on. So you can do that experiment and you come back to that, or you verify what this gentleman did for us. So now let's look at the basic principles here. That is the law. So it is this law we are coming to interact with right now here. So let's just go a little bit fast now. So we said that in your exam you are going to be given a glass block. So let's see, first in this experiment we are going to interact with the materials here. So some of the materials are as follows. I have the glass slab. This is the glass slab. That is the rectangular glass prism. This is a glass slab or glass prism. Now I have a few drawing materials here. Of course, you need a protractor. I have drawing pins here. These drawing pins, I will have some of the drawing pins that have been attached here. I'm using them as a softball pin to ensure that the paper doesn't fly. So I'm going to stick it onto this to affix the paper onto this. This board is called the drawing board. This is the drawing board, and that is the drawing paper. So we have the thumbnails. We can call these ones too also thumbnail, or we call them the pressing pins, which we use also to put notices on the notice board. So because it's going to a softball, we can also call it a softball pin. So now we have that, and I'm going to use this softball pin because of the colors of the softball pin, I'll be using them as optical pins, object pins, and image pins respectively. I'm going to be using them. So now let's check the other materials. I've got I have a few materials here. You have some drawing material. So let's check the experiment itself. Now we are provided with a drawing board. So let's say we have the drawing board and we have our drawing paper. So we are now expected to make an outline of the block. We are making an outline of this block. Let's say that is exactly what we are going to do on it. So it is the outline of the block I'm trying to take here. So when we come back to let's do it simultaneously as we move. We are trying to get the outline of the block. So let's say that's the block. Now I'm taking the outline. The outline of the block is just to pass your pencil right around that object. In other words, I want you to find the perimeter. The perimeter is the total distance around the shape. So we now take the outline there. So this is the outline of the block. So we've got the outline of the block. So this is how it is done. So you have got the outline of this block. So that's the first step. So that's what we've done there. We'll be demonstrating it as we move. So that is the outline of the block. So let's see. Now let's call the outline of the block ABCD. Yeah, ABCD. So now that outline of the block, you are expected to draw a normal there. If you want to draw a normal, then you can use your protractor. You can use your protractor if you care to, or you can use the compass. You also draw a normal. So I want to draw a normal. A normal is, maybe I want to draw a normal somewhere here. In some questions, you are given a particular distance, say 1/4 of this distance. So let's say this was 20 centimeters. I have to divide it by 4, so I got 5 centimeters somewhere here. Some of the questions will specify that position where you're supposed to draw your normal, but let's just use that point as our normal position in that case. So I'm trying to make sure I got a point somewhere there. Then I have a normal at the point, so this goes to that. Or I just put it here because of the space. I can put it somewhere there, here. So I got my point somewhere here. That is the 90. If there was a space there, I just put it here. Then I get the 90 somewhere there. Just 90s there. It goes right down there. Alright? Or you can put it this way, such that this point is there and you have this positioning. So this line is right on there, so I get this normal. The normal is always 90 degrees, so I get it this way, or I can go the other way, this way, to also get the 90 somewhere there, and I draw that line through. That is one way you can draw the normal. So now we get that. Or you still want to be, some guys who want to be so mathematical, they want to try this. So you can draw a semicircle somewhere here, a semicircle there, then you move to that semicircle, you strike that arc, you move there, you strike that arc, you move there again, you strike that arc, you move there, you strike that arc. So this junction to this junction will give you the normal. So you can draw the normal in so many ways. You can use your compass to draw a normal. Let's say I want to draw the normal at this point, so I'll do there. So with a small radius, I was able to cut an arc here and cut an arc there. Yes, so let's say I draw a semicircle there. If I draw a semicircle, let's just see. I want to demonstrate it there for you so you see. So I don't want to use that part of it, but no problem. So now we have a semicircle. I construct a semicircle there. Then I move there, I strike an arc there, strike an arc somewhere there. Then I migrate to that arc, I strike that, migrate here, I strike that. So now I can draw that normal. Yes, that's another way you can draw the normal if you want to use the compass, or you can use the protractor, just that. So it gives you the normal. So let's say that's my normal, to be precise. So now I have that normal from here there. It's going through. So that normal is 90 degrees. Okay? So this is 90 degrees. Now I've got the normal, so I can clean some of these, my arcs, because I'm coming to use other arcs there. So I want to clean that. So this is. So now we have that. So that's my normal. It's always going to be 90 degrees to the plane, 90 degrees there. So that is normal. So on this normal, you'll be given 2 pins. So let me use the board. Well, I might demonstrate this way, then we go to the real experiment. Let me just use the board to give you the principles on the board as we go. Now we'll be giving a set of incident angles. Yes, let's say you are giving incident angle, and now you are asked to find refracted angle. So let's say you have 20 degrees, you have 30 degrees, 40 degrees, and so on. So now with those angles, so it's a 40, 50, let's say 50 even. So you asked to find the incident angle. So with this normal, you now draw 2 rays. You now draw a line such that the incident angle becomes 20 degrees. So you can come back here, you see how you can put this to get 20. So on this line, I must ensure that it's already there. So this is it. Now this is my 0. So 0, 10, 20. So let's say that's 20 there. So this 20 for this angle, this is 20 degrees, this is 0, this is 10, 20. So on that 20 on your protractor, you get a 20. So let's say my 20 is somewhere there. So, or I can even go to 30 in this case. Let me take 30 in this case. So I just use 30 here. So let me put it back there so I get up to 30. So you have there normal. So the normal is still there. So I'm going 1, 2, 3. So I have 30 somewhere there. So this is 30, it's 30, so I put 30 here. So I will move this, come back there, then I try to join this line to this. So this will give me, this is the incident ray, and it is now 30 degrees from my protractor, from my own protractor. That is the eye. So I have got eye. Let's say we started off with 30. So let's say I started off with 30 there. So now I have this. So I've labeled this. So now you are supposed to take 2 other pins. Now after that, on this line, you now put 2 pins. So let's extend it properly there. So I must make sure that the distance between the pins is at least 4 centimeter between the pins, 4 centimeter, 4 centimeter there. So I use the object pins there, 4 centimeter between the pins. So now that's 4 centimeter, let's say somewhere here, and there 4 centimeter. So I used P1 here and P2 here. So that is what you're supposed to do with these pins. So when we get to the experiment, you'll be seeing I'll put 2 of these pins here, 1 pin somewhere there, the other pin there on the board. When I get to the board, I'll put those 2 pins there. I must ensure that the distance between them is 4 centimeter or above, not less than that, because if you want to know how straight it that line, you must ensure that the space is relevant between them. There's have enough space between them. So that is the the line. That on that line we have P, the first pin, the second pin. Those are the ones we will cross as we go to the point. So now light from that locality, or if it's fall on those pins, and the light from those pins is moving in air, because those pins were in air. So now when the light falls on them, the light is now moving from the air and entering this glass. It's entering the glass. Is now a transparent material, so that's the block in there. So when the light falls on those pins in there, that light is supposed to move from air. There's air around this block, so it's moving from a less dense medium, it's entering a denser medium, which is block. This glass block is thicker, so it's because it's entering inside a denser medium. You expect that this ray to bend and obey that law. The third law was that when it's moved from less dense medium to a denser medium, it's going to bend towards the normal. This is the normal. So now when we put it on the paper, you see that the light is supposed to bend in there. This is the block. So now I have that block. Now we expect it. So when it is going to bend, it is going to bring the images of this and these two pins inside this block. So this other phase is where you're going to stop. You're going to watch. So you look at this D and C and place two other pins. So we're supposed to look at this and place two other pins. Sorry, idea by parallax. We avoid parallax, that is the negative motion between the object and the observer. So you, after placing that pin, so let's say the pins are already there, I place my block. I'm supposed to look through here and see the images of these pins inside here, and those images of these pins inside I'll be able to look at by closing one eye. I now place along here. I'm not looking here or there. I'm going to look here, because the light that brought that image inside is going to refract. So as it is refracting towards the normal according to the law, so you now expect the images of this and this, some are here, because it must have refracted towards the normal. So let's say this image is there, this image is here, you put two other pins there, let's say some are here, and this other pins here. That is by closing your eye, one eye, so that you can avoid that parallax. You put two pins here, another pin here. So let's call those pins P3 and P4. That is another set of pins. The first ones were the object pins. Now you have placed these two pins. We send their images inside here. So what you're going to do, you're going to be looking at this part of the block there between here, so that you can see the images of this as it is found inside. You use one eye closed so that you see it properly. So there and there. Let's say you have seen the images of this, such that the images of these two pins and this other two pins outside are appearing to be in straight line. So they appear to be in straight line as you observe it. So you have human factors here. You have to be careful with that. You must be able to see that the images of these two pins, as you view them inside the block, that transparent block, they are supposed to be in straight line with the two pins you are going to put. And that is where the practical is. That's where the demonstration is. You must be able to get it. So let's say I was able to see the image of this and this, there are this and this inside the block. So it is now this and this and this and this are supposed to be in line. When you place these two pins, if they are correct, if the image is actually in line, this image of these two and this, if they are in line, you will not see those images, because these pins will block them, telling you they are in straight line. So they appear to be in straight line. So now they say remove the pins or remove the block. So we have removed the block. That is now the procedure. After watching these two and you have placed your pins, we have placed the pins here and here, as you saw the images of these two inside. Now you remove the pins, remove the block, and now join those two pins, those 2 points there you have got. So you connect these 2 points that you've got with a line. Let's see that's a line. So we're there. Okay, so that is P3 and P4. So to meet this point here and here, also try to draw a normal there as a normal, so that it can help you to get the angle of emergent. This one is the emergent ray. This is emergent ray, and you now have the normal, another normal here. So you have the emergent angle somewhere there. So now you try to link this point with this, so that's how you know how this ray was able to refract. So let's say there it refracted, bent towards the normal some way. So it's bent towards the normal. So it has bent towards the normal in that case. So now this is it. So we have the angle of refraction. So here it has refracted. It was supposed to go straight. If there was no block there, this is how it was supposed to go. It was supposed to go right straight. So here there. let's say there was no block, it was supposed to go right there, here, but it succeeded to move away from that direction and move towards the normal because of the law of refraction. It is because the light is entering an optically denser medium as compared to that. So now you now look at this ray that is coming, which was supposed to be the correct ray if there was no block. It's because light travels a straight line, it was supposed to go straight if there was no block, but because a block came, now you see that this ray and this are going to be parallel to each other. This and this are parallel rays. This is supposed to be parallel to the emergent ray. It's supposed to be parallel to this emergent ray. So now when it is parallel to the emergent ray, then we now want to see what is the lateral shift. So there's going to be a shift somewhere there. So that shift is, there have been a shift somewhere. So I'll be able to now draw a normal somewhere there. That normal must touch this. You must draw another normal there, such that I will have the distance between it's going to form, that line from this point to there will form 90 degrees. That distance is what is called the lateral shift. So that small d is the lateral shift, Now the lateral shift, and you'll be asked to verify this for several steps. So let's say we have E, we'll be able to find that, and you'll find D. In that case, this can take any letter, so in that case let me just call it let me call it D in this case, because I'm using D in another stuff. So this is the lateral shift. So we'll have this lateral shift. So we want to find that. So we'll be able to find the angle of refraction. Angle of incidence has been given to you. So with that angle of incidence, you'll be able to get measure, because if you connect this point to this point, you're able to find the angle of refraction here. And now when you connect this point to this point, you get this ray to produce it to meet this DC as a point. You're going to draw a normal. So that normal there with this ray will give you the emergent ray. So you can also discover this other angle, that is the emergent angle. So you have the refracted angle, that's the one here, and you have the incident angle which was given there. Now another reading you can get from here is you want to find the distance between, if there was no block, the light was going to go straight there, but because it's entered a medium that is optical density, it was forced to bend that way. So that deviation, that shift is what is called, in this case we call it lateral shift. It's not actually deviation, we call it lateral shift. It is moving from that line. So this distance between it can be measured also. You'll be asked in the exam to measure this distance between that. So you must ensure that this line goes straight, normal there, straight. We assume that there is no block. When there was no block, the ray was going to go straight there. But now because it entered a medium of different optical density, it is bound to move towards the normal and vice versa. So now you have received all the three reading or 4 reading you needed. So you'll be asked to repeat this experiment for 40 degrees, for 50 degrees, as the case may be. These are all manipulations you can do right now, but just note that you must ensure that the normal is perfect and the block is placed inside the normal. This is outline. So they will tell you first, get the outline, and now draw the normal, and now take the block and put it back inside the normal. Once the block is not inside, take the block and put it back inside its outline. When the block is not inside its outline, all other angles here, measurements will be wrong, because you have not placed the block. That is one important precaution. I ensure that I place the block right inside its outline. That's a very relevant precaution, because if it's not inside the outline, you will not be able to get these distances correctly and even this angle. So that is what you repeat for always. So we have already used this refractive index and we are able to get the lateral shift. Now we want to look at the refractive index proper. We want to find another way of getting the refractive index. So we can use the radius of a circle here. So now with this diagram, we now want to see what will happen with, we want to find the refractive index proper again. So we look at it. So you now open your compass to its convenient radius such that it can go round. So let's say this is my own radius. I go round there, right round there with that circle. So I go round with that circle. So I cut that circle somewhere there. So I've gone through, my compass is shaking, but no problem with it. Now you'll be able to get this circle. Now in some examinations you'll be asked to a specific radius of that, and once Sometimes the radius is open for you, like I did here. I just assume my radius. So it's possible that you'll be given that radius. But if you are going to repeat it for several angles, you must ensure that you maintain that radius throughout your experiment, because it is very important, because it's a particular fixed distance you are trying to measure. So this radius, if you are going to select any radius, you must ensure that it is going to be a fixed radius you continue when you want to do this experiment with 40 degrees, 50 degrees, any other angle there. So let's say I've done it for 30 degrees. Now that is it. So with that, I can now come in with I want to now draw some lines. So they will ask you also in the examination. Now, after drawing that, try to get a 90 degrees line, a 90 degrees perpendicular line. That line must be perpendicular. That is a line that is moving to where this line and this angle met. You must be able to get that. So here, this is that point. You must be able to get a 90 degrees over there, and you do the same for this, where the line met this curve you have drawn, where it met the refracted ray and also the incident ray. So you have got those 2 points. So this is, now you must ensure that it is also 90 degrees there, and this one is also 90 degrees. So let's call here E and F, and let's call here G and H. So I can also, from that linear shift, I can also find D, let's say the distance E, F, and I can also measure that distance G, H. Yes, so now this can be distances you can measure. So now you remember what I did. I took the compass with a convenient radius, I ruled that stuff, I went through with that radius, with that circle. Now that circle must have touched the incident ray at a point E. It has also touched the refracted ray at a point G, H. So now I'm coming to draw a normal, that is a perpendicular line, from that point of contact of the circle with the refracted ray. I draw a normal there, so I meet this normal here at 90 degrees. Yeah, so here also the same, the point of contact of this circle with the incident ray, that position there, I draw a line to meet that normal there at a point. So I take my ruler. This is what you do. Now you take the ruler and measure here, you measure there, and you also take the ruler, you measure here. Now you use your ruler so after measuring here, you now know that I can find GF, I can also find EF for different angles. You can repeat this for also 40 or 50 and so on. So now you check this out. Now let's say we have got that. Now we want to find the refractive index of this. So refractive index, let's say the normal here. So I have two triangles over here. Let's call here point O possible. So I have got triangle, that is a triangle, that is F and E, and I have O. Then I also have another small angle somewhere there. This is another angle. Yes, so I've got two angles so far here. So we have, this is G and this is H, and that is TRO. So we have two. So now this line here is what gave us this triangle. So there's a triangle here. So OGH is OGH. Now here also there's a triangle there. So now I have already got this angle. Let's call it angle of incidence. That's the one here. That was the angle of incidence. And there's angle of refraction here. That is the R. So I've got the angle of refraction somewhere there. Now I want to find, this is the radius. So let's call here radius. This is also radius, because this distance here, because it's the same circle, this distance must be the same distance there. So E to O is the same as O to H. So now that's it. So R, they're all radii. So you can come and do the math here. So let's look the sign here, the sign theta. So sign I in that case is opposite. That's the opposite of that triangle. This is equals to EF all over hypotenuse. Hypotenuse is sorry, but that can be written properly. We can call it that way, and this is R, that is it. So half sine I. Yeah, possible. So I keep that equation. Somewhere there. Now we have the next one here, the same. So this is opposite, that is sine R is equals to opposite, that is GH, opposite all over hypotenuse. You know hypotenuse is OH, and that is by extension GH is equals to R also. So we can have sine R is equals to GH all over R. That is the radius. So now we have got two equations here. So let's call this equation 1 and call this equation 2. So but we know that from refractive index was sine I all over sine R. So if I put this in perspective, I will now have refractive index as equals to sine I all over sine R. So I already have this sine I as what? This is EF all over R divided by sine R is GH all over R. So if you do the math here, you have refractive index is equals to EF all over R multiplied by R all over GH. Now this R and R will vanish, so we'll have L refractive index is EF all over GH. So let's see, I was able to measure here as this, my EF gave me 4 centimeter. And now the GH, of course, I expect it to be less than that other distance. So let's say it gave me 3 centimeter. So let's say this gave me 3 centimeter, and now this gave me 2 centimeter. Yes, I expect these two distances to be different because this length is obviously longer than this. So let's just say this is my measurement was 3 centimeter and this is 2 centimeter. Now if I put it right here, now I come and put it right here, I'll have EF for that angle was 3 centimeter and GH for that same angle was 2 centimeter. So when I punch that, I'll have 1.5, which might be the refractive index of this block. So and the refractive index of this block maybe is 1.5. That's one way we'll be able to find the refractive index of the material using this experiment. So by this calculation, you must have been able to now get. So in the examination, I just did it for one angle 30. I just measured up to that, but you'll be given series of angles there and you'll be able to repeat it so that you get the correct reading somewhere there. So I've basically explained how refractive index connect with lateral shift and also how refractive index connect with lateral shift, and I'll be able to find refractive index by a different method here by using the geometry here, that is Pythagoras or Socrates in that case. I was able to find here, remember this is opposite over hypotenuse, so you can look at how I went to that point. And now let's come to the precautions that you took into consideration. You ensured that the block was right in there, and you ensured that you had a sharp pointed pencil, because if your pencil was blunt, you're able to have these angles will be different, the diagram, the angles will be wrong or different because of you are going to add. If the lead is so thick, it's good to add on the angle or even reduce the angle. So you must ensure that you have a sharp pointed pencil, and you ensure that also the image was actually in that is the most important one, because you must ensure first of all that the pins you are placing, they are in straight line with the images of these two pins as you observe them here. You don't observe this way or this way. You must, and that is the experiment, you must ensure that the images of these two pins inside here we are observed through here, and you ensure that the two pins you place we are in the same straight line as the images of these two pins as you observe them inside the block. You know, it's a transparent block, transparent material, so that is a very good so you'll be able to ask, you'll be able to explain the Snell's law and get to that point. So let's keep watching. Now we are now coming to the application on the experiment on the paper. So you see all what I've done here is what I'm coming to demonstrate here for you just now. So let's see. Yes, so what I've done on the board is basically explain the theory. Now I'm coming to apply it on the board. So what I was trying is that you also take your own materials and you now follow up as you construct together. So now we are told to first of all make an outline. So ideally you must be able to have some of these materials on your own table. You have a couple of drawing materials here. So I have the first here. Let's see, I have already drawn the outline here. This is the outline. You're able to pass the pencil right. You found the perimeter right down there. That's the outline. So we got our outline. Now, if the question says you are supposed to actually draw this normal 1/4 of this distance, then you have to measure all this distance here and you divide it into 4. So let's say I wanted to do something like that. Now let's say I just want to let me because of time, let me just use this point as my own normal, or some other point somewhere here, I get my own normal here. But in some questions, you'll be asked to divide this into 4 equal parts and take one part and draw your normal there. So now let's say I have this position as my normal, so I can draw my normal from there. So you get to put your protractor so that the pin is right there, and this line is right on that point, so you get your 90 degrees right there. So you see this what the long line here, the black line, must correspond with that your outline, so that you get it correctly. Now I locate the 90 from that point. That's the 90, so we're there. So 90 there. Now I'll be able to draw my 90 from there. So you can use a ruler, you get through there, that is 90 through that point. So let's say I've got my normal here, and if I want to verify that I got through there, I go measure it so that I get the correct position of the 90. It's 90 normal. So I have drawn my normal from that point. It's 90 degrees here. So now that is the normal. So now I have got 90 degrees somewhere there. Now I wanted to find the 30, this angle. I said let it be 30 degrees there. So I'm going with the 0. I go right through there. This is the positioning. I put it right here. This is the angle. Here, this is 10, this is 20, this is 30. So it's 30, I put it right here. This is 30. Then I use my ruler, or I can use this part of the protractor. I get there. So I now have, so this is my 30 degrees. So on that, this is 30 degrees somewhere there, and this is the normal. Remember, this is O. So I'm using the lettering here as I go. That is O. So I've got the outline A, B, and I have C, D. That's C and D. Yeah, so I'm ensure that the outline is fitted here. This is the block is there. So I come to ensure the block right here, so that it's in there. Yes, it's fitting. So now on this pin, I have to make sure the spacing between the pins is reasonable. So I said I wanted to take force of less than more than 4 centimeters. So let me just see here. So I have that. So I make sure there is a distance between them. So I put here, I put one here, and I put the other one somewhere there. So let me just select those points. So reasonable spacing. So I'm spacing them reasonably. So I got the first pin somewhere here. I put the other pin somewhere here, so that they're reasonably spaced, So those 2 pins are, this is object pins. I put them here, and this is one pin and another pin there, the same position. You see the distances between them is all the same. Yeah, so I have those 2 pins somewhere there. So these 2 pins here, the space between them is, yes, so you have the space between them is reasonable from that point there to there. It's reasonable, same space. So now I say replace the block. So replace the block right in there, and now you come watch through the face DC, so that to ensure that the images of these 2 pins are seen inside this block. You put 2 other pins such that the images of this and the 2 other pins are going to be in straight line. That is where the experiment is now. So I advise you inter-alia that you have to ensure that you close one eye to avoid parallax. So now you are looking through DC. So in the day for the exam, you can just drop down you go down a little bit so that you can see how the image of these pins are seen is here. So you can see that if you look through that, you see the image of this is over here. The image is, so when I put these pins here, so I've seen so now if you look at this, you discover that the images, the 2 pins there, if you look at this keenly, you see that these 4 pins are all in straight line there. This is this, and the images of the 2 inside, when you look at it, they are in straight line. So if you look at right there, you will see that they are all in that straight line there, the images of these two. So the two blue pins there have their images somewhere there and there. So I place two other pins, this green, so that the images of these two inside the block are in the same line with them. So I now found out that that is how you ensure before you even remove the block, you try to see whether it's actually in line. When you put them, you see that the images are all in line there by closing your eye. So you see that it's right straight in there. So you see they're in line right there. So now after doing that, you now you have already done the experiment. If you're sure that the images of these two pins are in line with these other two pins, then you have already done the experiment. Now they say remove the instructions on the questions or whatever, you go with it. You say remove that block, so you remove the block. You say also remove the pins, remove the pins, remove these other pins. Now, but these pins, the points where these pins are very important to you right now, because you need those points. So let's say the points are this and that. So now I take my ruler, I try to connect those 2 points somewhere there, those 2 points to that point. This is it. So I join the 2 points there to a point somewhere there. So I've got them here, So now they met at a point. Now I connect this to this. So you can see that this line came because of these 2 points. So these 2 points are the ones that I produced them to touch this at a point. Then I'm able to draw another normal somewhere here. You draw another normal there. So I use my protractor to get another normal somewhere there. So I use that to draw another normal so that it appears to be, the normal is somewhere there. So that is another 90 for me there. So I got a normal right through that point. This is a normal. So I just got a short one in that case. So now we have the normal of that guy. So now we look at the protractor again and try to measure this. This was the angle of refraction. This is the refracted ray. So we want to measure this angle of refraction. So now I can put it right here. I can measure this way. If you can do it that way. You just put it there. So that the line, this point is on this and straight there. And that part of the protractor is that on that junction here, and you have this line here. So if it's on that line, you can count from here. That is, this is 10, this is 20, this is 20. So let me say this is approximately 19 point something, so it's 20. So I have 20 somewhere there. So it's almost 20 degrees. So I'll be able to get here 20 degrees. So now with that 20 degrees, that is my R. So with that angle, so I come back here. When it was this, what was this? This was 20 degrees. So now I can come back and measure. If I measure the incident, I'm going to measure the angle of emergence. So the angle of emergence, you can put it there and measure as well. So if I put the angle of emergence over there, this is, I just ensure it is at that same point there. Then I look at my scale again. This is all right. So it is 30 degrees. This is 30 degrees. So I have the angle of emergence as also 30 degrees. So I have 30 degrees. So you have seen a kind of relationship that is developing here. This is 30 degrees. This is 20. So if you look at this, you see now that from this, so let me just show you what I've done so far. I have done the rays. Yes, this is the incident ray. So the light move from that incident ray, and that's refracted ray, and that's emergent ray. So now the ray of light entering this block, bend towards the normal, obeying the law, and now in moving from the block, going out, that's the air, it moves away from the normal, that's the law of refraction. So the third law is already obeyed here. So that's what we have done so far. I've got a couple of readings. I've got the refracted angle here, and we have the incident angle here, and we have got the emergent angle. So I've done this only one angle, that's 30 degrees there. And now I want to now look at it in another way to verify the same refractive index using that. Remember, I used the approach of this circle and I got the refractive index. Now I want to use another approach here, that is the I and the R approach to get the refractive index. So let's get this. This is sine I, let's say 30. This is 30 degrees. yeah, and sine R is 20, so we have sine 20. So let's say I have, this is 0.5, I think so. So sine 30 is 0.5. If you punch from my calculator, so we get my calculator is giving me a lot of problem here, but let me use another calculator. So I'll use another calculator there. So you can also use your own calculator and verify this. This is sine 20. This you have sine 20. This is sine 20. You have sine 20. Yes, this is 2 and 0. Wow, so there is sine 20. Let me just go back there because this calculator is kind of this is sine 20. I can't see the 2 right now because the calculator's 0. Okay, so sine 20, what is the answer? So it gave me 0.3420. that is 0.3420. So if I punch that from the calculator, so let's say I have 0.5. I can see the numbers here, but I'll try as much to help myself out. This is 0.5. 0.5. This is 5. Yes, so that's this calculator is not too good, so have that. But if you punch this, actually you discover that you're going to have 1.4 something. So you have 1.5 as well. So you punch that, use your own calculator and punch that. If you punch that, think you can get that answer there. My calculator is not responding right now. So but we have the refractive index and the lateral shift as it goes. So you'll be given another, if it's a continuous exam, you have to do another set of trace, another set of outline with different type of angle. So you can get that in another position here. You construct another one here, there. You try to get an outline to that, and that's for, I want to do for 40. So I can do another one here for, yes, like that. Because when the paper is exhausted, you can turn it over. During your exam, so you'll be able to do that. This is a trace. This thing you have done is called trace. So sometimes you are required to take this trace and attach it onto your answer script, and you present it, because if you are going to tell the examiner that this is, well, 20 degrees, the examiner must be able to check whether this 20 degrees is actually correct. So that's why you are supposed to ensure that all the angles are good there and are measured clearly. This trace must be attached to your work as the question demands, so watch out for this. Let me just make a small emphasis there with respect to the thickness. Now the thickness of this block is not this, it is not this. You know, the word thickness is somehow confusing. So the thickness of the block is not this. In this experiment, the thickness of the block is actually the distance which the ray of light travels through the block, and the ray of light is traveling through this block here, that is moving from this point to there. So this is the thickness. BC is the thickness. In other words, the breadth of this, not the height. This is the breadth. That breadth is what is called the thickness. So this is the width of this is the width, which you call the breadth of it. So now take note of that. It is not this that is the thickness. It is this thing that is the thickness, that is the breadth, that is the width of it. And that is where light travels in there. So let me give you a summary here. This ray is always going to be parallel with the emergent ray. And the emergent angle is always equal to the angle of incidence, as you have demonstrated it here. You can see that the angle of incidence is equal to the angle of emergence. That is telling you 30 here, 30 approximately. Maybe you can have an error difference of 0. Plus or minus 0.2, but it's always supposed to give you the incident angle, is always supposed to give you the angle of emergence together. So we will continue this interaction again. So what you can do is to actually go to your lab now and try to figure out these numbers and see, you verify what I've done here as I've also done for you here. You verify that in your own lab. And I want to thank you for your audience, and keep watching as we move along with the practicals. Well,